So Awan, and today the paper that I'm going to present is towards a general intelligence and interface for wearable health data. Let's start by reading the abstract. So did you guys read the abstract? What do you think is the gap sentence?
Two sentences started with specifically and moral.
Yeah, I also think the same. So these are the gap sentences in which they mention why they needed to do this and what are the mislimitations. So let's start with why we actually need the wearable health data. So basically, there are number one reason is that the billions of devices nowadays worldwide. So there is a lot of data that we can obtain from the wearables. Then another reason is that we can use it 24/7 to monitor the longitudinal data. And also there is a massive amount of real world time series data. So these are the reasons that the wearable health data is promising, and also the wearable data captures rich signals across different domains. So, like we can get the activity information, heart rate, oxygen and temperature and sleep information, and they provide the abundant, continuous, multimodal real-world data at population scales. So, the issue is that although the wearable data is quite abundant, but the labeled health outcomes are quite scarce. If we look at the today's pipeline, we have the wearable sensor signals. Then normally what nowadays scientists do is that they hand engineer the daily summaries of these features, and then they use the one of the supervised model for the single health outcome, and then they get the sum of the predictions. So basically what they do is that they use single model for a single outcome. So what are the reasons that this pipeline can break down is that basically it is really costly and infeasible. The second one is that it can't really represent the population level phenotypic diversity. And the third reason can be that it has heterogeneous baseline health and physiological across individuals. So we can't really get the personalized outcomes, and there is no shared substrate or like the endpoints between the models. So the core problem is that although we have abundance of the wearable time series data, we don't really have a lot of high quality health labels. So what happens is that because of this imbalance, nowadays the foundation model approach is quite attractive to solve this issue. So first, what happens in the foundation model is that first it learns from the large scale unlabeled variable data, and then it adopt the learned representation to many health outcomes. So why do we think that foundation models are the next step is that the large scale, we have a large quantity of unlabeled variable data, and then it can learn the one general representation from that large scale variable data. And after that, we can use it across many health outcomes, not a single one. So, however, the issue with the foundation models is that although learning a general variable representation is like not a whole story, there are still two bottlenecks that needs to be addressed. So we will be going to see what are those bottlenecks. So first one is that we have finite pre-training scale. So our current pre-training data is quite limited and it can't really incorporate all the diversities and modalities and the longitudinal coverage of the data. And also another one is that there's manual downstream. Like although we do the embeddings and all that stuff, but at the end, each of the endpoint has to be manually engineered for a specific outcome. So the question arises is that can generalizable features be learned from wearable data that can help diverse the individual across diverse health applications? So in order to answer this question, the authors introduced the sensor FM that scales the wearable pre-training to learn the general representation. But the issue still remains is that, but learning the one reusable embedding doesn't really eliminate the need to design a separate prediction model for each downstream health outcome. So to answer that, they also automate the downstream automation adaptation with the LLM agents. So after getting the downstream health domains, they also use the downstream adaptation with the LLM agents. So together with the sensor FM and the agentic classroom of the classroom of LLM agents, they provide the complete solution to the both issues. So now after using the LLMs, they have task-specific prediction. So we will see what is the architecture of the sensor FM. So basically, sensor FM is trained on over 1 trillion minutes of sensor data with almost 5 million people's data across hundreds of countries. And this data is used for the pre-training purposes of the sensor FM. And then we have the almost 14,000 held out subjects across 3 perspective studies, and these are used for the evaluation of the sensor FM later on. So we have basically 35 discriminative tasks that will be used to evaluate the performance of the sensor FM. These are basically demographics, lifestyle, cardiovascular, metabolic, mental health, and sleep. So basically what happens in the sensor FM is that the model basically gets the 24-hour window of 34 1-minute aggregated sensor features. So there are total 34 sensor features that comes from 5 sensor modalities that are PPG, accelerometer, EDA, skin temperature, and altimeter. So from these, they have 7 categories that they use, and using these 7 categories, we have 34 1-minute aggregate sensor features. So if we look here at the example, we can see that there are some of the data that is missing, like the device of wrist, or is like the device is out of power, or the device sensor was off. So we will see how they deal with this kind of missing information. So basically, what happens is that uh, first they treat the mass reconstruction with the missingness. So we will see how they basically do it. Simply, we have the information, then they normalize and they remove the outliers, and then they use the like must input and they add it to the encoder. And after that, the embedding and the decoder decodes it and it goes back to check how well it performed by using the reconstruction loss. So basically, it is the similar architecture that we have seen still so far. But how they deal with the missing data is the important one. They use the adaptive and inherited masking that was mentioned in the you et al. In 2025. So what they do is that we have input information that already have the missing data. So next is that they introduced some of the points. Points and they introduce the artificial missingness like the masking. So then they combine both artificial and the inherited um, maskness and they make the final data. From that, they use the dropout removal. They remove some of the points from that and also they use the attention mask. So they use the dropout removal and then they use the attention mask. And after that, they enter that information to the encoder. So from now, that information, the encoder will have the visible mask, and then we will have they will reinsert the dropout tokens, and decoder runs and reconstruct it again. So it is just a summary of how they basically deal with the missingness of the information.
Right.
Yeah.
Great.
Inherited masking
And the artificial mask.
so inherited masking is basically the already missing data in the in missing information in the data, and the artificial masking is that they introduce the missing data so that for that purpose they know the information of that missing information. So then they use that information to kind of guess how well it is performing in getting the missing information.
Can you explain the attention mask?
So basically, what happens is that we already have a data that is have missing information. Wearable has that a lot. So from the missing information, the authors introduced the artificial masking, in which they introduce the missing information of the in the data, and that information they already know. So that kind of work helps them evaluate how well the model is performing in getting reconstructing the original data. So they combine both the information and then they have the adaptive and inherited masking. And from that, they do the dropout removal. They remove some of the information that was masked. And also they use the attention to mask some of other information. Then they introduce this information to the encoder, and then using the decoder, they get the original reconstruction of the data. And for the last, they only check the artificial mask because that is the information they already had.
So that figure, that one, I think the one corresponds to the position where no neither of the mask are like.
Yeah, it is the already available information. So it is like not the masked information. Zeros is the masked.
Is there any reason why they do drop out removal and how this drop out removal drop out masking is inserted to the encoder decoder structure?
So basically, actually, this is an whole another paper. So I checked that it was basically for the computational purposes. They drop out, so they lower the cost of computation.
and then did they just input the dropout mask input, or how they reinsert that dropout
So basically, they
for
first,
decoding?
yeah, for decoding, they reinsert those dropout tokens so that it can learn from it has the information of the previous masks. So basically, they don't really impute the data. So that's the main part of this architecture. Yeah.
The other mask already proposition work as mentioned by Aqsa. That paper talks about the reason why the original data is in poverty. If there's no information about past in past layer of the relationships, then if the input is weak, ask part of the latent layer of no information, then it could have regenerate the original data. But if the input is powerful to inform only with the mask latently the variable, it can extend the unbounded latent variable that the decoder has some information but the missing data, so decoder can regenerate the original data. The original purpose of the decoder is to empower make the even if the mixing data then regenerate the originally representative data in the instance.
So I will move forward. Then after using the sensor FM, they retained sensor FM. Basically they freeze the encoder, and then they aggregate the information to the person level and they use the non-missing tokens only for this purpose. So from that, they also applied the dimensionality reduction with and then they also optionally added the demographics to help in the classification task or the regression task. This is actually just a summary of how they do it. It is mentioned in really detail in the paper. So it is kind of how they do it. This is just a general idea.
How the regain is
So basically, they just, to be honest, I am not really don't know a lot about it because there are some points that I still don't understand in the paper. But they at the when they have the embeddings, they aggregate the personal level information, and they only use the non-missing tokens of information of the person, and then they repeat it for all the subjects at the the embedding is the person level, like if I'm correct about it. Then they use the aggregated embedding, and then they do the PCA. So that reduces the variance and it matches it basically matches the embedding dimensionality to latent sparsity. And then after that, they also kind of add the demographics to make it more personalized, like age, sex, or like the race of the participants, and then they concatenate that information and use that information for the classification or the regression tasks. Mm.
For token, what is the size of the info? Wow.
So basically, it was, I think, 20 into 1. So I think I removed that information, but like it had 20-minute window. Yeah, I think 21. Yeah, what the best.
Then for one day, when you do 3 times 24 tokens.
Yeah.
And so another question is, one token from the data, we need all of the sensor
Yes.
inputs. If one data is missing, we cannot.
So actually, they have kind of like strategies to deal with that kind of information. So actually, this paper was really in, like, it had really detailed information about how they deal with the missing data. So they actually had references to different papers. So they hands of missing data information, and they how they deal with it. They also mention in those papers. So it's kind of like, oh my, okay. So then they evaluate the results, and then they have the matrices for the tasks. So they aggregate the results across 5 different folds, and then they report the results. So I know it is kind of confusing. So if anyone have any better opinion, then it will be better.
Here, price valuation is only for the downstream. So we are only, I mean, the encoder itself is just for its value.
Kind of, yeah. So after this, does anyone have any question?
Is there any data sets for this value?
No, like for the evaluation, they have like they mentioned that they use the held out data before, like the almost 14,000 users, then they perform it for the.
I mentioned this because so the step 2 aggregation to person level things is it uses a lot of information by taking the average. Like maybe one way to prove this is using attention architecture to make AI learn which accommodation friendship. But I think they didn't use it likely due to they don't have enough data. Or I think the non-labeled data to train the foundation model is very large. The labeled data is not
Oh yeah.
makes it very small. That the disease is for
they will move forward. Then after doing all this, they use the set of LLMs. So basically, after getting, we have the data set that we already saw that was labeled. So now we have labels, variable embeddings, and demographics information for the data set. Then they give the instruction prompt to an assistant. And from that, the prediction had basically have 5 student LLMs. That there are basically different versions of the Gemini. So they have the basically the cycles of this information and they generate the code and then they execute that code and check how well it is doing and give the feedback and then repeat cycle by cycle. And another thing is that they also have like the agents collaborate with each other and also have like the collaborative discussion kind of thing. And then they basically do this to get the prediction of the health outcomes on like this. So this was the second bottleneck. So they answered using the series of LLMs.
So they they do kind of classification prediction things with LLM.
Kind of they have the information from sensor FM and then they incorporate that information into the agents. So basically the prediction task is done by the
Apply.
agents. Yeah.
So agent does the work of our work.
Yeah. So agent is like the we can say machine learning expert.
Ah, cute. Does the students LLM and teacher LLM are the same model? Are they the same model or do they have some difference?
No, there is difference. The teacher LLM is I think is the higher level. So after that, if we see, they basically use the agent, the sensor FM as an agentic AI. So basically, they have the information from sensor FM, and then they insert that information into Gemini, and then they get the final outcome for that. So this is how this whole sensor FM augmented like agent works. So they also tested the how well these were performing. So they had the clinicians to evaluate the results that were obtained from the prediction by the agents. So basically, there were 3 types of like one was we have the demographic daily data and sensor FM information, and then the other one is that like the ground truth. It doesn't have the sensor FM information, and then we have the demographics and the daily information. So the 4 clinicians actually evaluated this performance and check how well it was performing in terms of context and justifiability and these matrices. So there were almost 18,000 ratings for that. And then if we look here, we can see that the darker part is when they say that it is performing really well. It has the highest rating. And with the dimming of the color is the how well it is not performing. So if the color is dim, then it is not performing well than before. So we can see that most of the time that the information with the demographics, daily metrics, and the sensor FM predictions work better than just having the demographics and daily matrices. And clinicians approve this. basically that's all for the architecture of the sensor FM. So basically it had most of the time it had information from other previous works. So they just kind of aggregated that information and made the sensor FM to be able to work well on the unlabeled data. So the main idea was that they used a lot of information to pre-train the sensor FM, and also the using the agentic AI, they kind of have the predictions for the health outcomes. Anyone have any suggestion or question on it?
Clinicians will see kind of prediction information.
Yes. So they then evaluate how well the predictions are.
What is the daily metrics?
Daily metrics is the daily information of the, like the daily minute by minute information.
It's embedded vector.
Yes. Then they kind of evaluated how the different kinds of, this is a lot, but like they evaluated across different parameters. We can see demo only is like it only have the demographic information. Then we have these are different models with different set of parameters. So if we can see that the baseline model is the most of the time it is the highest performing in different classification tasks and the regression tasks. We actually have the information of these models later in the slide in the appendix. So and then they also check whether the how the classroom with the like the LLM agents is working. and also the classroom and with the demographic informations. So we can see that most of the time, if we look at the classification task, most of the time it is outperforming the other models. And even in the regression task, and if we look at the sleep disorder treatment, we can see that it is performing quite well in comparison to the previous, just using the reference.
Kind of rough information they use.
Basically, they had the age of the person, then their sex, their race, and also like their BMI. These kind of informations they had for the demographics.
Basic.
Yes, yes.
Provides a slip. That cases.
So basically,
Correct.
so basically, it is like the when someone has the sleep disorder, then they give their own treatments like the medication or something. So it is that.
Maybe not evidence this parents. Yes.
Yeah.
Very emotion. 이거는 기본적인
문과 대한 유사한 학부인 그렇죠. 맞습니다.
그러니까 이상의 거를 주는 거는 프런트에 걸친 서비스 이런 것들 맛이 너무 좋다. 스무 보다
아, right.
straight.